Great.
You can go, maybe.
Okay, thank you very much. Thank you for helping to organize this nice workshop. So my name is Christos Georgiadis. It's in Greek, sorry for the difficulty to pronounce it in French. And I'm a PhD student under Professor Matl in UC Louvain. And I will talk today about bipartite quad and hex domination. So, we follow an indirect approach for meshing. We first obtain a triangulation, and then we try to combine it either to quad mesh or hex mesh, or hex dominant mesh, basically. So the general pipeline, the steps for a quad mesh method, is to generate the points that are embedded on an input triangulation in an advancing front manner, and this we do by utilizing crossfields. We can triangulate these points with local modifications of the input, so it's an easy and robust way to obtain a triangulation of the generated points. And finally, we want to combine pairs of triangles to quads to get a full quad mesh. Now, respectively, for the 3D, we can, again, generate the points inside the volume, take a constrained Delaunay triangulation of these points, and with the same reasoning, combine TEDs onto hexes. Of course, in 3D, this is much more difficult to do. So today I will focus mainly on both these C points, let's say, of combining, and I will try to explain a way to make our life a bit easier, maybe. So we understand that this is not the most optimal. I mean, this kind of indirect method is not the most optimal way to go. You get all these front collisions, you get remaining triangles, etc., but it has certain advantages. So we will see. So following, we have a necessary condition for a quad mesh is that the domain should be bounded by an even number of edges. This is we know of it. And if we see this example here, we see that we have a domain that is bounded by an even number of edges, but still, if we combine two triangles of those to a quad, we will get some remaining triangles that cannot be transformed. Okay, there is a well-known theorem that explains these things, and in general, you can imagine that in every case we can get this kind of remaining triangles or topologically bad regions inside our domain during point generation. So there is this paper that tries to solve this problem of combining triangles to quads by computing this kind of perfect matching. That is basically the optimal way to find the pairs of triangles to combine onto quads. So we want to make our life a bit easier and to create the points and the initial triangulation in this way that we do not even have to compute this thing. So the idea is we want to identify and eliminate this potential odd-sized region. And the idea is to use some kind of topological index for the points. So we can see, for example, in a simple quad, we can label the edges of the quad with opposite indices. And this condition holds for the general quad mesh. We can say that we want this kind of quad mesh that can be colored this way. This is not new. It's a two-colorable bipartite mesh. There is a similar idea that has been explored already in 2014. So going back to our previous example, we will see that if we index the boundary points this way in a bipartite fashion, we get a triangle that it has three same indices. This gives us a hint on where the problem is. Okay, we can after easily split this triangle to get this topologically consistent layout. And after we can just, we already know our quad match there. We can simply reposition the point according to the opposite labeled indices and immediately get a quad mesh. So the whole idea is that during the point generation, each point, starting from a boundary that we can color the points, each point generates one with the opposite label. So essentially, we propagate some kind of topological information throughout the domain, along with a geometric one that is the position of the points. To show it better in a working example, a simple one, we can see here an initial triangulation with the embedded points that are colored. I don't know if it's visible. The coloring like blue and red points. So this is the right-angled triangulation that we take. Obviously, we can see all the problems of the advancing front method. We can see the front collisions, etc. But still, there is a nice way now to identify all these kind of bad triangles, split them, reposition the vertices, and immediately get a quad mesh. So essentially what happens here is that in this step, we can just take all the edges that have the same index, and these edges are essentially the perfect matching of the quad mesh that Blossom had tried to solve. Basically, the perpendicular. Yeah, so this way we can get quad meshes very easily in a variety of examples. I mean, theoretically, it's always working. Of course, it's still an unstructured thing, and here in more detail. And I mean, here's a very complex example that we obtain a full quad mesh at once. So it's good. Essentially, all these things works as a error correcting code in some sense, that we can immediately find all the bad things that happen during the point propagation. So following on, what about the 3D problem now? Maybe we can use some kind of similar idea. So of course, it's not a matching problem like previously anymore. It's a very complicated thing. Here we can see all the possible triangulations of a cube. So we don't really have an idea on how to fix or how to add this kind of points to fix our thing. It's not trivial at all as previously. Furthermore, even this, we have the same condition of a hex mesh, but we can obviously see that the diagonal here is also an edge that we would like, but we don't want. So things get very, very difficult here when we try to use this kind of thing to combine the TETs onto hexes. So I thought, I was thinking of a lot of ideas to solve this or to tackle the problem in another way. For example, there are we can use this kind of labeling that comes from the using network topology. But still, there is not an obvious way to generate this kind of label. So the whole idea is that if we were able to have some kind of indexing that carries more information than just the bipartite condition. But still, we could experiment a bit and see if we can at least improve the cavities, the remaining cavities of non-combinable TETs on the final hex dominant mesh. So we modify the search of possible hexes in Pellerin et al., the work that is done on our lab for the combination of TETs to hexes. And we modify this in order to accept only edges that have this, that follow this constraint, that are of opposite label. And if we do this, of course, it's faster because the search space is much smaller, and obviously it gives a much lower percentage of hexahedra. Not very much lower, but still lower. It's not the optimal. But still, it's not what interests us. What we want is to see if we can make the remaining cavities more easy to handle, to manipulate after. We know that there are two topological conditions for hexahedral meshes. The one is that we want an even number of quads bounding the domain, and the other is that we do not want any odd cycles. So we try to see if there's a way to satisfy this kind of conditions in order to make from the big problem to go to smaller cavity problems that satisfy this condition, and maybe after we can eliminate them somehow. So it's a work in progress. I just will show you some small examples. So for example, here we have a hex dominant mesh obtained with this kind of method. Now this is very ideal in some sense because the starting quad mesh is compatible. We use the scaled crossfields, the scaled 3D crossfields that my colleague Alexander Saman will present later on. But still, if it seems nice, if we extract the interior cavity, it's an ugly thing that is this one. And again, there are all these fronts that collide and all this mess. It's much worse in 3D. But the idea, as I said, is to see if we can make this kind of cavities easier to split, easier to manipulate. So, for example, here we can see, now again, this is a very nice example. It's one of the few. So on the left is the combination without these constraints, and on the right is with these constraints. As you see, on the left, obviously, we have two more quads, two more hexes, excuse me, that go inside this thing. On the right is not permitted to do this, so it does not. Also, you see on the left, there is this kind of, in the bottom left of the finger, there is this kind of prismatic things that essentially we avoid with this kind of bipartite condition. So the whole idea is to obtain the kind of cavities that on the right. Now, this is not very trivial still because we encounter a lot of issues. For example, you can always get this kind of spiral configurations. Essentially, they signify that a lot of fronts collide at this point from different angles and different. Yeah, but maybe it's a way to explore. Huh? So yeah, I think that's all. So going back to our initial slide, that we have these three main steps of the method. We can add some extra points on 2D of quad mesh. For quad mesh, we see that we can add an extra point to eliminate this kind of topological inconsistencies. On 3D, the equivalent point, I do not really have an idea. I mean, I know, for example, that like in 2D, if we had in 3D a TET that has four same topological indices, this would be a wrong TET to have, but I cannot really go further than that with this kind of labeling. And an extra step would be maybe to get just better cavities. I mean, it's the same in 2D. If we just combine the X's with this bipartite, the quads, excuse me, with this bipartite conditions, the cavities that are not combined in 2D will be even-sized cavities. Yeah, I don't know if all these are understandable till now. So anyway, I will conclude with some key notes. So it's a pipeline of independent steps. This gives us a certain kind of flexibility. I mean, like it's totally independent. We generate some points that are embedded on the triangulation. We can use a crossfield, a scale crossfield. We can use a different size map. We can do anything we want. Again, the same is for the triangulation of the points for the combination. So we have an easy way to always get full quad now. Also, it can be used to just convert a quad dominant mesh to a quad mesh without doing the subdivision, the Catmull-Clark subdivision. It's still unstructured, of course, because the method is an advanced broad method. We have an excess of singularities. Now, if we follow crossfield, the singularities of the crossfield naturally arise on the final mesh, but there are much more than that when sizes change, when fronts collide, etc. Maxence will later on present a very nice thing to make the singularities minimal and improve the structure and the quality of the meshes. Yeah, and finally, maybe there is an opening here to tackle the hex meshing complexity by making it simpler to begin with, like making this kind of conditions to make it simple. Yeah, so that's all. Thank you very much for your attention. And if you have any questions, I'm open.
Thank you for your presentation. So if you have any questions, don't hesitate. So maybe I will start with a small one. On the 2D case, when you insert a point, do you have any guarantees that on the quality of your hexaedras? I know that it's not structured, but are your hexaedra at least some good?
The hexaedra or?
Sorry, the quadrilateral. The quads. Sorry. In 2D.
This is strongly dependent on the crossfield, in the sense that, I mean, even if we don't have a crossfield, even if we do axis-oriented point generation, we will get something that's acceptable, is always valid. But if the crossfield is good, we get good quality meshes. The only thing with if you see in very complicated models that you have a lot of size features, etc., you may encounter some small things like doublets that can be easily fixed, or like flat quads on the boundary that you cannot move the boundary node, but still you can push this kind of singularity inside the domain. So yeah, no, in general, it's good quality.
Okay, great. And it's available in GMSH?
In an experimental way, yes.
Okay. Okay.